So today we're going to start lecture 19 of CS229, and the topics for today, we're going to talk about the maximum entropy principle and how the exponential family distributions that we saw earlier in the course can be derived from the maximum entropy principle, and we will show how under what conditions maximizing entropy is equal to maximizing the likelihood, MLE. And also this will kind of lead us into some interesting topics such as calibration. We'll briefly talk about calibration and what calibration means and how it relates to maximizing entropy, etc. Very interesting topics. And then depending on how much we cover and how much time we have left, we will talk about a few variants of the expectation maximization algorithm and how these variants kind of leads itself into some of the more recent advances in unsupervised learning, such as variational inference and the variational autoencoder. I'm not sure whether we'll be able to finish variational autoencoders today or even start it, but if we don't finish it today, we'll pick it up in the next class. All right, so before we dive into today's topics, a quick recap of what we covered in the previous class. So in the previous class, we covered PCA and ICA. PCA is principal components analysis. In PCA, we are given data xi, which lives in a d-dimensional space, and we are to find a low-dimensional subspace Zi, which lives in a space of dimension k. Right? For every Zi, we want to find its projection onto the low-dimensional space that we call Zi. And the way we go about doing that is to map x to xu, where u is a column vector of k columns, where each of the column are the top k eigenvectors of x transpose x. Right? And by doing this operation, we effectively get the projections onto this subspace. And then we talked about independent components analysis. In PCA, our goal was to find a low-dimensional subspace, whereas in ICA, our goals are very different. In ICA, our goals is to find independent sources that explain our data. And the assumption that we made were there are d different independent sources. We call them Sj, where j indexes the source number. So each of the Sj's is sampled from some probability distribution Ps, which has to be non-Gaussian. You can either use the Laplace distribution or the logistic distribution, any distribution which is kind of has mean 0 and it's non-Gaussian. We saw some intuitions of what happens if we have Gaussian, if we make an assumption about Gaussian distributions as being the source, we get this problem of rotational invariance. And so as long as the sources are non-Gaussian and we have some square matrix A, which we call as the mixing matrix, which mixes the S's into observations. So S's are unobserved, X's are observed, right? And our goal is to start with X and recover S, which are the independent sources. And the way we want to do it is to, the relation here we assume is that A is a square invertible matrix, and we want to invert A to get W, and W is the matrix that we want to estimate, so that given observations we can multiply it through W and recover the original independent sources. Right? And the way we go about doing that is with maximum likelihood, where we directly estimate W, and we saw that the probability of x can be represented in this way, where we map x back to W, x back to S using W, and we need a corresponding Jacobian term, log or the log determinant. And by performing this maximization using gradient ascent, there is no closed form solution for this. By performing gradient ascent, we can recover upon convergence the unmixing matrix W hat. Right? And we also saw this in the homework. Hopefully you guys have finished this question in your homework. If not, no problem. We're just stating the results here. The homework question has a small introduction about about some explanations about KL-Divergence and entropy and so on. You don't need to know that for the purpose of this lecture, but if you've already seen it, it's helpful. So we define the KL-Divergence between two probability distributions, right? So this is something important, right? So far we've seen things like the distance between 2 points in a vector space, right? Here the two things between which we are measuring are probability distributions, entire distributions, right? So you can think of P being some distribution like this and Q being another distribution like this, and we are trying to ask what's kind of the difference between these two distributions, right? They're not single points but entire distributions. So the KL-Divergence from P to Q is defined as the expectation with respect to P of log P by Q. You should note that this is not symmetric, in the sense the KL-Divergence from P to Q is not the same as from Q to P. If they were the same, we could have called it a distance, like KL distance, but it is not symmetric. And this is the definition of KL-Divergence. This is closely related to concepts such as entropy. So we define entropy of a probability distribution as the expectation under P of log 1 over P itself. So the entropy kind of measures how spread out a distribution is. So if we have a distribution over some finite support, a probability distribution that is uniform over them is considered to have high entropy, right? Whereas if another distribution over the same support puts all its mass on any one point, then this distribution is considered to have low entropy, right? So entropy, you can think of entropy as a synonym for uncertainty, right? High entropy means high uncertainty. You believe that the point can, some data observation can come from any of these. You're not sure. Whereas a low entropy means low uncertainty, right? If this distribution tells us that the point that we're going to observe next, if you were to sample from this, will be this particular point alone, right? There's almost zero uncertainty there. So this is considered to have low entropy, right? And then there is also this nice interpretation of cross entropy that's there in the homework description. You can see that, where we replace P over here by a different distribution Q, right? And the cross entropy is gets this form, expectation under P log of 1 over Q. And the difference between the cross entropy and entropy is basically actually just equal to the KL-Divergence itself. So the KL-Divergence between two distributions PQ is just the cross entropy minus the entropy. There are some nice interpretations about this in terms of coding theory that's there in the homework, but that's not really necessary for our lecture today, as long as you kind of remember these formulas. And also earlier in the lecture, earlier in the course, we came across exponential family. The exponential family is a way to characterize a family of probability distributions, where the probability distribution over y with some parameter called natural parameter eta takes this form, right? So here b of y is called the base measure, right? And there is the exponent of some term over here. That term has two parts. One is eta, the natural parameter, dot product with t of y. So t is called the sufficient statistics over y, minus a of eta, where a is called the log partition function, right? And we also saw again in your homework 1 that the mean of this probability distribution can be represented as the derivative of the log partition function at eta. So if we change eta to two different values, we get different means, and the way you go from the parameter value eta to the mean of the corresponding distribution is to calculate a prime, or the first derivative of a of first derivative of the log partition function at the parameter value eta. And it so happens that this function a prime will always be invertible, and so we can go from the mean of a distribution back to the natural parameter eta this way, right? So the first thing we're going to do today is to derive maximum likelihood estimates of eta given some observations y, and then we'll jump over to maximum entropy and start seeing its equivalence. Any questions on this so far? Yes, question?
In ICA, the result, is the log determinant going to act as regularization, or are we going to regularize on top of it?
So the question is, in ICA, is the log determinant acting like a regularizer, or are we going to add regularization on top? So that's a very interesting question. In ICA, it so happens that most of the time we are not really interested in generalization error, right? So ICA is kind of in a way different from the rest of the algorithms that we've seen, where in the rest of the algorithms we're interested in generalization error. Whereas in ICA, we take some examples, fit a model, and just recover the sources of the given data itself. So it's not common to use regularization in ICA. And this log determinant is actually not a regularizer. Right? This log determinant is a necessary component to make the distribution a valid probability distribution. Good question. Any other questions before we jump into MLE of exponential families? Great. Okay, so MLE of exponential family. So in the when we studied exponential families earlier in the course, and when we studied GLMs, we made this simplifying assumption that y was always a scalar in our case. So in case of regression, y was just real values. In case of logistic regression, y was a binary 0 or 1. We saw some generalizations with softmax where y could take multiple values. But now we're going to take an even more generalized form where y can be y could be anything, and t of y, which we always most of the times when we studied GLMs, t of y was just taken to be identity as y itself. But now we will again relax that and make it even more general, where t of y could be anything. So suppose we have an exponential family, right? Exponential family, p of y given eta equals b of y times exponent. I'm just rewriting the same thing over there. Eta the product t of y. So this is the dot product. Eta can be a vector, and t of y can also be a vector of the same dimension, right? And this is just the inner product. If these two are scalars, then this is just a simple product minus a of eta, right? And we are given some data s equal to y1, y small n, right? So we given this data, and we want to find eta, eta hat MLE equal to argmax. So here we assume IID, right? Argmax across eta log I equals 1 to n p of yi eta. Right? This is a standard maximum likelihood procedure that we followed throughout the course. There's nothing different here. Right? Now let's simplify this further. So this is argmax with respect to eta. Now log of the product is the sum of the logs. So I'm going to take the sum I equals 1 to n, and the log goes in. So the log of this thing over here will give us log b of yi, right? Plus log and the exponent cancel, you get eta dot t of yi minus a of eta. And in order to do maximum likelihood, we take the derivative of this with respect to eta, set it equal to 0, and solve for eta. Right? The same process. So for this, we now take the gradient with respect to eta of this whole thing is equal to, so this is going to be sum I equals 1 to n. The derivative of b of y with respect to eta is 0, right? So this will be just 0 plus the derivative of eta dot t of yi with respect to eta will be just t of yi plus t of yi minus derivative of a of eta with respect to eta is, we'll just call it a prime of eta, right? And this gives us, so so we have a sum over I from 1 to n of this term, and we set this equal to 0. This gives us n times a prime of eta. So this is n, this is eta, right? This is n, the number of examples, and this is eta. They look kind of similar. Equal to I equals 1 to n t of yi, or a prime of eta is equal to 1 over n I equals 1 to n t of yi. And this tells us eta hat MLE is equal to a prime inverse of 1 over n I equals 1 to n t of yi. So what just happened here? The maximum likelihood estimate of the natural parameter of any probability distribution in the exponential family can be calculated as the mean or the sample mean of the observed Cepheisian statistics taken through the inverse of a prime. If you remember in the exponential family notes, we called g equals a prime to be the canonical link function, and we called g inverse, which will be a prime inverse, to be the, or I think we called this the canonical response function, and this to be the canonical link function. Right? So this is just the canonical link function. So take the sample mean of the observed yi's, run it through the canonical link function, and that gives you the maximum likelihood estimate of eta, where this is in the most generic form. Right? So when we take specific members of the exponential family, like the Poisson or the Bernoulli or what have you, a prime will take some particular form, t of y will take some particular form, but in the most generic in the most generic setting, this is the estimate for the maximum likelihood estimate of the natural parameter. Okay, yes, question?
In the last class, we were doing ICA and unsupervised. What's like the goal for today? Why are we doing this?
So good question. So in the last lecture, we were doing ICA and PCA, which was unsupervised learning. So what's the goal here? That's a very good question. So today, what we are doing is trying to understand this, a pretty generic concept called maximum entropy principle, and how that results in concepts such as calibration and KL-Divergence. And we will use KL-Divergence as a concept to kind of understand variational inference and variational autoencoders. So this, I would not call it either supervised or unsupervised, because these are just maximum likelihood estimates of general probability distributions. This has I wouldn't call this either supervised or unsupervised. These are just exponential family distributions. Good question. Right. So this was the maximum likelihood estimate of the natural parameter, and let's just save it, because we will refer to this shortly in a few minutes. Now let's switch gears and talk about maximum entropy. Right. So So the maximum entropy principle is a principle that tells us that whenever we want to estimate a probability distribution with some observed data, let's suppose we have a probability, probability distribution over the real values, right? So this is R and X, and this is P of X, right? So and suppose we make some observations on X, right? So we observe this, and we observe this as samples from this probability distribution, and our goal is to now estimate, what the density of what P of X is, right? And given just 3 points, it's very hard to tell, what the density of P of X is, right? Ideally, what we would like to have is, an infinite number of observations, preferably, an uncountably infinite number of observations, so that we can precisely calculate the fraction at each point and construct some kind of a density, right? But we are only given a finite number of points. They could be large, they could be small, but we are still given a finite number of points, and we need to estimate the value of P of X at every point X. And the maximum entropy principle tells us that the way we want to go about it is to first translate these data points into constraints, right? So for example, the mean of these set of points could be, say mu hat, right? So mu hat, is just the sample mean, right? Similarly, the variance could be n equals 1 to n xi minus mu square, right? So this is just the and if we take this to the mu hat, this is just the sample standard deviation, right? And the maximum entropy principle tells us that our estimate for P of X should be a probability distribution that is subject to these constraints, and these are hard constraints, and within the family of probability distributions that satisfy these constraints, choose the one that has the highest entropy, right? So the constraints, we can call these constraints, right? The constraints define a set of all probability distributions that are what is also called as feasible, right? Any probability distribution that satisfies these is a feasible candidate for our estimate, and then among this large set of feasible probability distributions, the feasible probability distribution will almost certainly be more than one, because there are an infinite number of probability distributions that satisfy, in this example, a particular mean and standard deviation. Among the set of all feasible distributions, choose the one that has the highest entropy. That's what the maximum entropy principle tells us. And the way we go about formulating it is P, which is the estimated probability distribution over Y. To clarify some notations, let's call this Y, and we'll be using Y instead of X, right? So P is equal to argmax over all P's, maybe we can just call it P star, argmax over all P's, which maximizes H of P, which is the entropy, right? H of P is just the entropy that we defined here, such that we have some constraints. So the constraints, we will write them in the form, we will limit ourselves to linear constraints. By linear constraints, what I mean is such that the sum over J, or the sum over I, Tj of Pi is equal to some Ci. What does that mean? So we will assume that the constraints for our estimation problem are given in the form of some functions t's which are indexed by j. Yeah, t's are indexed by j. So t is some function that takes y to r, right? So the constraints that we are given, constraints such as these will be given in the form of these t functions where we have n such things or m such things. So j equals 1 through m, tj of y to r. What does this exactly mean? It means that for every corresponding tj, there is a corresponding cj, the constraint value, where we need to satisfy sum over I equals 1 through n tij tj of yi is equal to ci. Now, if tj, if for example one particular t of y, if we consider this is equal to just y itself, then this gives us a constraint for the mean. Because this basically boils down to for I equals 1 through n t of y times, I also forgot p of I. T of y times p of y is equal to ci. C. So this is just if t of y is equal to just y, then this becomes I equals 1 through n y times p of y is equal to the expectation of y. Right. So for different choices of t's, or rather the different choice of sufficient statistics, we can express constraints in this form. And we are also going to assume that the support of y is finite. Right? This support for y being finite is a simplifying assumption, and we don't really need this to show the results, but we are going to assume it is finite so that we can represent things as inner products and sums rather than integrals, right? And we assume that n is the kind of size of the set y. Yes, was there a question?
These were very natural constraints like gain and our variance. How can there be any other kind of constraints just given the data?
So how can there be other kinds of constraints? So generally the constraints are constraints given are of the form where the some kind of a moment of the observed data is equal to some value, right? So the moments of the distribution should match some the moments of the observed samples. Generally, those are the kind of constraints we are interested in.
Why don't we directly use these constraints in this form? Because we can just take the form of our exponential family and then using these constraints try to make constraints on the parameters b and eta.
Well, so when we so the question is, why don't we start with here? So the exercise that we are trying to do right now is to start from the maximum entropy principle, make no assumptions about the form of p. Right here, so far, p could be any kind of a probability distribution. We are just assuming some kind of a support, and what we are going to show is the maximum entropy principle will recover the exponential family. That's our goal over here, right? And intentionally, we are using the same symbols, t's and y's that are going to end up being, the corresponding terms in the exponential family. So the t's over here are trying to satisfy some constraint. Right? Eventually, by the end of this exercise, we will see that t's will be the sufficient statistics. But for now, just assume t's are some kind of a function whose linear combination with p must satisfy a constraint value. So we have, so n is the cardinality of the set Y, and we have m constraints, right? Which means we have m such t functions. And now our task is to perform this optimization. Right? So we want to maximize the entropy of the probability distribution such that some kind of linear constraints over P are satisfied. So this, let me write this more clearly. I T of yi j times P of I is equal to C of j, where j equals 1 through m. So there are m such t functions, and all these t functions must satisfy this this kind of a constraint where the expectation of t is equal to some constraint value c. And most of the times these constraints will be arising from data, from the observed data, right, where Cj will be equal to 1 over n, where n is the number of examples, I equals 1 through n, t of yi j. Yes, was there a question?
Yeah, for a bit confused about notation there, right below the definition of Cj. So there's I after, the y bracket.
There's an I over the y. Oh, yeah, you're right. So, thank you. So this is, so yeah. So to clarify the notations, there are m such t functions, and each of those m is indexed by j, right? And tj tells us, it's the jth t function, and I is the index we use to scan the support of y. Right? So y, there are capital N elements in y, and I equals 1 through n, t of yi. So every possible value of I will get a probability of pi. That's the probability of so pi is equal to p of yi. Right? So we're going to switch. It's very common that we switch between the functional notation and the vector notation, right? They mean the same thing. Right? So we are given a set of linear constraints, and satisfying these linear constraints, we want to maximize the entropy. Yes, question?
Check, the I is of j, right? Ci. It's not Ci by Cj. Right, yeah, after P.
Oh, this? Oh, sorry, yes.
And also, is support for y basically each individual data point that we have?
Yeah, so question, so what is the support of y? So here we are assuming y has finite support, which means y can take on a finite number of values, right? So y itself can live in a high dimensional space, but we assume y can take on a finite number of values, right? And p of yi tells us the probability that our distribution assigns to that point yi. Our observed yi's, y superscript, parenthesis I, are the actual observations. So y superscript I tells us what the ith observation was, right? If you sample many of them, but each of these yi's will be one of the finite numbers of elements in script y. Yeah? Exactly. So this is just a way of saying that we are only interested in discrete distributions. This question?
For continuous, would we require compact support, or?
We would compact support over y.
Yeah.
So for example, so for continuous, this could be the entire R line, real valued line. It should. Yeah. All right. Any questions in this? Let me repeat it. There were a few typos. So just to repeat it so that everything is clear. we right. So we assume that y has finite support, which means there are n. N is the size of the cardinality of script y, right? And our probability distributions are assigned over this space. Now we are given some observations, small n number of observations of yi's, and out of these observations we can construct constraints. Right? So the constraints can be, for example, that the mean of the observed data has some particular mean. It could be that the sum of the squares of the observations is some value. That could be another constraint. It could be the sum of the cubes of the observed values is some value. That could be another constraint, right? So t of y can be things like a t of y equals y, t of y equals y square. They are different possible functions of y, and out of those functions we construct these constraints that this constraint basically tells us that the mean of the distribution P will have to be the mean of the t function of a particular t function should be some particular value and so on. Right? Now, subject to these constraints, now we want to solve this optimization problem. The way we go about solving this problem is to construct what is called the Lagrangian. So if t, the t function is, if that is still a little confusing, you can assume t to be to generally take on two values. The most common values for t are t of y equals y and t of y equals y square. Those are like the most common kind of constraints that we come up with, where we want to say the mean is something, the first moment is some particular value and the second moment is some particular value. But here we are trying to derive it in the most general form, where t could be anything. And so using these constraints and the entropy objective, we will construct the Lagrangian. So the Lagrangian L of P, eta and lambda. So this is the probability, the variable for the probability distribution itself, and eta and lambda are Lagrange multipliers, and the Lagrangian will be h of p plus the inner product of eta comma tp minus c plus lambda times inner product of 1 p minus 1. What is this? So here p is our probability distribution. You can think of p as p1, p2, pn, where n is the cardinality of the set y, and t is a matrix where we have t1, a row corresponding to t1, so that would be t1 of y1, t1 of y2, t1 of y capital N, and similarly we have m such, so tm of y1, tm of y2, tm of yn. So this is small m, the number of constraints, times n. N is the cardinality of y, and this is n. And our constraints say that the inner product of this with this should be equal to C1 until Cn. right? So this matrix times this vector equals this vector is capturing the set of all constraints under which we want to operate, right? So this inner product is like the expectation. So each row times a column is basically the expectation under P of T1 of y, expectation under P T2 of y, and expectation P Tn of y, right? So this vector is equal to C1 through Cn, right? So these two are equivalent ways of writing. Yes, question?
Yeah, so the C's and the T's are like, we decide those, like we decide to compose those. What are the P's, like where do we get the P's?
So P's, so the question is T's and the C's are the constraints that we choose to impose, that's correct. And the C values are generally evaluated from data, right? So given some data, we see what the empirical values of the C's are and make that the constraints. What is P? So P is the probability distribution itself that we are trying to estimate, right? So P must satisfy Pi is greater than or equal to 0 and sum over Pi, I equals 1 to n should be equal to 1, right? So P is the probability vector that we are trying to estimate. And the way we want to estimate P is such that it maximizes the entropy and satisfies these constraints.
So let's say P2 in that column vector, it will be the number of times you observe y2 in all your y's.
So is P2 the number of times we observe y2 in all of your y's? In the long running average, yes, the number of times we will observe y2 across all y's. So P2 is just the probability of y2. Now think of P2 as equal to of y2.
And is it possible, so most of the time we want, like we take a discrete sample from a data generating process, like we would ideally like to take infinitely many samples, but is it possible to put an interval on the C's instead of like hard values?
No, for now we're gonna talk about only point values of C's, right? Right, and so this is the set of constraints, right? So Tp minus C is the set of constraint that should be equal to 0, and this basically tells us. So this is the entropy that we want to maximize. This is for the constraints from data generally, right? And this is to make P a valid probability distribution, right? So we construct this Lagrangian, and we pretty much just solve this optimization problem from this Lagrangian. Right. So to solve this Lagrangian, we start with taking the derivative of the Lagrangian with respect to P's, and we get a partial with respect to Pi of the Lagrangian, and this is equal to the partial with respect to Pi of h of P plus eta times Tp minus C plus lambda times 1 P minus 1. Right? and now we differentiate this with respect to pi. So h of pi is sum over all sum over I, p of I times log p of I, right? So all the terms except the ith term can be eliminated. So pi, this will be minus pi log pi. We are ignoring the non-I terms because they're going to cancel with pi anyways, right? Plus Tp minus C and 1 p minus 1, right? And when we take the derivative, what we get is apply the product rule, taking the derivative of this with respect to pi. First we differentiate the first term times the second term, and then we differentiate the second term times the first term. So that will give us minus log pi plus the derivative of log pi is just 1 over pi. 1 over pi times pi is just 1, plus this will be just the inner product of eta times t of yi plus lambda, right? So what we're doing is, when we are in this expression, which is basically Tp minus C, pi will appear only in the ith column here, right? So this ends up being eta, and C will just get cancelled with pi. So this will be just the inner product of eta with t of yi, right? And from this we basically get that we want to take this derivative and set it equal to 0, which means we get take so log pi is equal to lambda minus 1 plus inner product of eta times t of yi, and this gives us pi is equal to e to the lambda minus 1 times exponential of eta dot t of yi. Right? So right away we see that p of I seems to be taking some kind of an exponential form, right? And the reason why we get this exponential form is because in the entropy we have this log term, and when you set log of p equals some value, p will be exponent of some value, right? That's the reason why with entropy, when you're trying to maximize entropy, the presence of this log term in the entropy will kind of naturally result in an exponent coming when we solve for pi. And now we have this, and we want to solve for lambda, and solving for lambda is pretty easy. So we have pi equal to this, and sum over I equals 1 to n, pi equals 1, which means the sum over this entire thing, e to the lambda minus 1 times exponent eta times t of yi, this should be equal to 1, and so e to the lambda minus 1 will be 1 over sum over y in script y exponent eta times t of y, right? So we got p to be in this form, and we can eliminate lambda by making use of the fact that probability distribution should sum up to 1, and that gives e to the lambda minus 1 to be that value, and so we get the final form of P of y to be so let's call this denominator to be, let's call this as z of eta. So we get P of y is equal to exponent of eta times t of y divided by z of eta, where z of eta is just this normalizing constant, and so P of y parameterized by eta is equal to the exponent of eta times t of y minus a of eta, where a is just equal to log z. Right? So z is called the partition function and a is called the log partition function. Right? And by taking the log, we can bring it in into the term. Right? So here we see that by just by just following the maximum entropy principle and trying to recover P, where we did not assume any kind of form for P, right? We just assumed P was can take any values subject to it just being a valid probability distribution. We see that by having only this constraint, maximizing the entropy of P to satisfy the constraints that we observe from the data, we recover the exponential family that we recover the exponential family form for P, that P of y will always be in the form of the exponential family, basically. Yes?
So in our math, why did we do this step of sum of pi equals 1 when we already captured it in one of our constraints?
So this, what we did here is basically enforcing this constraint. That's what we did. I'm sorry?
Do we have to do it explicitly again, or should it already be factored in the math?
So the question is, should we explicitly do this, or is it already captured in the math? So if we don't have this constraint, then p's can be any arbitrary value, right?
Also, and why didn't we use entropy as our objective function? Like, are there other versions of doing the same?
Yeah. So the question is, why are we maximizing entropy? And there is a reference in the notes that's been posted, which goes into why maximizing entropy is kind of a natural thing to do. So basically, this maximum entropy principle has also connection with statistical physics, where where the entropy has actually the same mathematical form. And in fact, there's a paper by an author. His name is in fact the same author of the link that's given here, Edwin Janes. He has an old paper called information theory and statistical physics, and that basically draws this nice connection between information theory, or the Shannon's entropy, the entropy that we have here in information theory, and drawing connections to the thermodynamics entropy in statistical physics, and both of them kind of follow the same maximum entropy principle. So it's kind of a natural thing to do. Yes, there was another question. Yes. So here, yeah, so the parameterization was always there. I just didn't write it here. So A of eta. So so P of I is basically equal to P of yi, right? So P of yi is equal to this times this, and this is equal to 1 over z of eta. Right? So P of y is equal to this divided by 1 over eta, 1 over z of eta, right? And z of eta is the partition function, and in place of z, if we instead take a of a is equal to log of z, then a will just go into the numerator. Next question.
Why do you want to maximize?
Yeah, so maximizing so the question is, why do you want to maximize the entropy? So maximizing the entropy, there are arguments to say that by maximizing the entropy, we are kind of being least committal in terms of our assumptions. which means the only constraints that we are enforcing is that the data that the observed data that we have are the only constraints that we are doing. Any other objective, if we maximize any other objective, it can be shown that we are kind of imposing further assumptions that may not be, may or may not be valid. In order to get the most unbiased estimate of P, then the right thing to do is to maximize the entropy, which means make everything else as uncertain as possible, subject to the only the observed constraints that we have.
Is there a link to maximum likelihood?
Yeah, we're going to come to the link to maximum likelihood shortly. Right? This question.
So you said entropy can be thought of like as the variability or the uncertainty.
Yes. Yeah.
Can it like crudely be thought of as the variance? So you want to capture as much variance from.
Yeah. So the question is can you think of uncertainty as the variance? The short answer is no, and there are good reasons why variance is not always equivalent to uncertainty. So there is a link to a chapter in the notes that's given, chapter 11 from the book Probability Theory, and that actually has some pretty convincing reasons why variance is not the right thing to maximize for.
Okay, and two more questions. In L, what are the last two terms?
So these two are the Lagrange multipliers.
No, on the right hand side.
These two. So these two are the terms in the Lagrangian that corresponds to the constraints, right? So one constraint is based on the data that we have, and the other constraint is that P should sum to 1.
Why is that how you frame it? Like inner product of 1 and P?
So inner product of 1 and P is
this sum of P. Okay.
so that's the inner product of the 1 vector and P.
And the second one?
The second one?
Yeah.
So the second one is T of P minus C. So we want T of P equal to C.
Got it.
Right? So T of P minus C should be 0. And this is the Lagrange multiplier corresponding to that constraint. This question?
Different from the large n? Like, is large n the size of all the large n?
Yeah, so the large n corresponds to the support of the of y.
Like the given set,
And small n is you can think of it as the number of observed data points.
large n
Is the support of
so every possible one.
yes, every possible y. Okay, so large n is the cardinality of script y. Yeah.
Why do you take the inner product of TP minus C with eta? So I get that TP minus C, but then like going with the last term, shouldn't it be just some, like let's say some new multiplier times TP minus C, inner product of that?
Well, so I will not go into the details of this. This what we have here is correct. If you have any more questions, post it on Piazza. I can help clarify it there. But this is the correct formulation of the Lagrangian. Right. So so we get that P of y will always take this form, where T of y, which were basically the constraints, end up being the sufficient statistics of the exponential family, and eta, which was the Lagrange multiplier of our constraints, end up being the natural parameter of the exponential family, right? And a of eta, which is the log partition function, is essentially the partition function that we get by applying the valid probability distribution constraint, right? So maximizing entropy gives us the exponential family as a natural consequence. We made no assumptions about the functional form of P when we started out maximizing the entropy, but as a consequence of performing this maximizing entropy subject to some linear constraints, we get the exponential family as a consequence. Right? So, was there another question? Yes.
For any data set, is data, like for any data set, are we going to get an entire family, or can we bind data to P1?
So the question is, for any given data set, do we get a different family? So good question. So the family that we end up getting is going to depend on the choice of the sufficient statistics that we choose. Right? For a different data set, we will get different values of C's, right? But the choice of the constraints that we chose to enforce will decide the family of the exponential family.
But if you have 5 points, let's say, and you impose the same constraints, are you going to get one distribution? So like how do you find eta given we just chose?
So we're going to come to estimating eta now, right? So the functional form of P will be in the exponential family if we start off by maximizing the entropy of P subject to some constraints, right? So now the question is okay, so we saw that the function the probability distribution will belong to the exponential family, but what about the estimates of eta itself? So for that, now let us to calculate eta. So first we solved it with respect to pi. Next we will do it with respect to eta. Right? So with respect to eta of L is equal to gradient with respect to eta. H of P is just minus sum over y, P of y log P of y, plus I'm going to write this as the inner product between eta times Tp minus eta times C plus lambda of something. And now we will make a few more observations. So this is the gradient with respect to eta of, so here this is basically the sum over y P of y times log P of y. So we saw that P of y has this form, and when we take the log of this, we just get the term inside the flower brackets. So it is P of y times eta dot T of y minus A of eta plus eta times Tp. So what is Tp? We saw that Tp is just the expectations of the individual sufficient statistics. So this I'm going to just write it as expectation of P of T of y minus eta times C plus lambda of something, right? So now take the derivative inside, and here we get so this sum over y P of y times something is like taking the expectation of this. Eta and eta will cancel, so we can write this as minus so take the eta out, so this will be eta times sorry, so we still have, let's still keep the derivative with respect to eta. So eta times expectation of T of y, and here we are taking the expectation of A of eta, but there is no y term here, so this will just be A of eta. This is plus eta times expectation of P of T of y minus eta dot C plus lambda times something. Right? So this and this cancel, so we get with respect to eta of A of eta minus eta dot C plus some constant C plus some lambda times something, and this is equal to A prime of eta minus C, and this should be equal to 0, and this gives us A prime of eta is equal to C, and these constraints are things that we generally want to estimate from data, right? And so we get eta hat is equal to A prime inverse of C, and that means A prime inverse of C, which we want to be like the empirical averages from data. So that would be 1 over n sum I equals 1 to n t of yi, right? And this estimate you will see is the same as this estimate. So the last step here, so from here, here we got that A prime of eta, which is A prime of eta should be equal to C, right? Is it clear until this step? Yeah. So eta should be A prime of inverse of C. Now what is C? C were the constraints that we started with, and usually these constraints come from data, right? So these constraints will be the actual, sample means of the corresponding sufficient statistics, and you plug them in here, the sample means of the corresponding sufficient statistics, and we get eta hat maximum entropy to be equal to the same expression that we get using MLE. So here, so the question is, what is t here? Yes, t here is, you can think of it as the vector of j functions. Exactly right. So what we basically got is that maximizing the entropy subject to some constraints of sufficient statistics that are whose values are obtained from the data is in fact the same, gives you the same solution as starting off with an exponential family where the sufficient statistics are the sufficient statistics of that exponential family and performing maximum likelihood on it. So this equivalence between maximum likelihood and maximum entropy is turns out to be one of the few interesting results in this area. Any questions on this? Yes, question. So a function will or the a prime will always have an inverse. This question.
We saw that a prime for any exponential family evaluates to mu or mean, like that's a property.
Yep.
Can we not use this property here to infer more conclusions about eta estimate of eta? Because it seems like a ratio of average of all the observations divided by the mean. Because
so a prime is the mean of the probability distribution. And basically what we are telling is that we want the mean of the probability distribution to be the sample mean, is essentially what we're trying to say here. So CIs were the means of the data. So here we are trying to say model mean equals sample mean.
and that was derived somehow.
Yeah, we got this from the maximum entropy, right? So we are still deriving the Lagrangian of the maximum entropy objective. And by solving for eta, we end up with the same estimate for eta as we would have if we had started from exponential family directly and chosen t's to be the sufficient statistics we are interested in. Yes, question?
My question is about the very last step. So
Here?
in the red box. So when we said C is equals to 1 over n sum
Mhm.
of the yi's, aren't we constraining like all C's to be some kind of average of like all C's?
Yes. So for in this setting, we are interested in linear constraints, that is linear in P, which means we are only interested in things like moments of the data or the moments of the distribution.
When
That's
we
right.
do that, is that like will that incorporate? So initially our C's were a weighted average of our T's, right? Not
C's were a what?
like we were weighing them by the P's, right?
C's were not weighed by the P. C's were just the observed.
C1 will be T1 Y1 P1 times T1 Y2
Right? That's the constraint that we want to enforce, that C1 equals T1y1 times P1 plus T1y2 times P2. That's the constraint that we want to enforce. But C1, the value of C1 itself is estimated from data.
And that has to be some kind of an average of the two.
Yeah, this is what we would choose to seize according to this. Exactly. Yeah. All right. So we've seen that maximizing entropy is the same as maximizing likelihood. And in your homework, you've also seen that maximizing likelihood is also the same as MLE is also the same as minimizing the KL divergence between the sample data and the model. Right? This is in your homework, question 2 or 3, the last subpart. And this is equal to max entropy. Now the connection between maximizing entropy and minimizing KL divergence is also called the max and duality theorem. Right? For those of you who are probably more interested on the theoretical sides, then to kind of learn more about this duality theorem, you might want to look up the maximum entropy duality theorem. All right. Now let's talk about a very related, somewhat related topic, which is calibration. Right? So calibration is this concept that, so for example, when we studied logistic regression, we saw that the output of our logistic regression model was, we took the inner product between x and theta, where theta was some kind of a parameter, ran it through the logistic function, 1 over 1 plus e to the minus x, and as the output, we got a value that was always between 0 and 1. Right? And we called that value, when we did y hat equals 1 over 1 plus exponent of minus theta transpose x. Right? So this will always be between 0 and 1, right? Which superficially looks like a probability, right? Because it's a value between 0 and 1. But what will make it a probability, right? Superficially, it's a value between 0 and 1. And then we, in order to use it as a classifier, we decided to use some threshold and call everything above the threshold as positives, everything below as negatives. But what will, why do we want to think of this as a probability, right? So probability is all right. So let me pose a question to you. What do you think is probability? Yes, go ahead.
If sum of all the y hats will be 1, then we can think of it as a probability.
Yeah. So if sum of all the y hats equals 1, I would still call that a superficial requirement for something to be a probability. Yes.
The value of the probability is representative of it, how often it occurs.
Exactly. So the value of y should be somehow representative of how frequently we, y hat ends up being this in for example, the data that we have, right? So and this property that the estimated probability values kind of match with observed frequency of occurrences is called calibration, right? So it is very common and highly recommended that if you actually build a logistic regression model, that you also plot this calibration plot, right? So calibration plot will look something like this. Predicted probability, and here this is observed frequencies. Now let's say this between 0 and 1. Take your validation set. in your validation set, assume it's reasonably large. You have a few thousand or 10,000 examples in your validation set. Take your model and run every example in your validation set through your model. For each example, you get a particular y hat, right? So you get a y hat, and there is a corresponding yi, which is the ground truth, right? Now, y hat will be a value between 0 and 1, and y will be either 0 or 1, right? And then your y hats will be, points that are distributed in this interval between 0 and 1. Now, next, chop this interval between 0 and 1 into, say, 10 bins, maybe 100 bins, doesn't matter. So chop it into bins. Commonly, it is 10 bins, but it could be any number of bins. And collect the yi's in each bin separately, or the y hat i's in each bin separately, right? So the set of all examples that have a y hat in this that is assigned a value in this range, take those examples and calculate the mean of the true labels of all the points that fall in this bin, right? And plot the true mean of the or the mean of the true labels on the y-axis corresponding to this bin. And ideally, what you want is to get a plot that looks like this. Which means for all those examples that got assigned a probability of, say, 0.99, we want 99% of them, of those examples, to have the true label as yi. For all examples that had a predicted probability of close to 0.5, we want the true frequency of the labels or the frequency of the true labels to be close to 0.5. This kind of a plot where you plot the predicted probabilities versus observed frequencies is called a calibration plot. And if your model gives you a calibration plot which is a straight line, then you call your model to be well calibrated, which means the predicted the output y hats from your model, you can actually think of them as probability estimates. If this line is not a straight line, then the predicted probabilities, you can't really think of them as probability estimates anymore. It may still be a good classifier, right? You may still be able to find a separating threshold and assign zeros and ones, and you may get a high accuracy. But it may not be a good probability estimate, right? So this concept of calibration, so calibration tells us, it's a statement about the quality of y hat being an actual probability. So if you have a model that predicts the probability of whether it's going to rain tomorrow, and take and you run it every day, and you have a few thousand days of predictions, right? Now take the set of all examples, or the set of all days where the predicted next day probability rain was, say, 80%. And then look at the data and see what fraction of those days did it actually rain. If your model is well calibrated, then the fraction of days that it rained the next day should be approximately 80%. It shouldn't be 90, it shouldn't be 70, it should be 80 for it to be well calibrated. Next question.
Two questions. If it is a good classifier, why do we care if it is a true probability measure or not? And secondly, if it is not, a 45-degree line, what can you do to solve it?
Yeah, so good questions. So if all we care about is a good classifier, then why do we care whether the predicted y hat is a valid probability or not? And the reason is because whenever you're building a machine learning model that predicts something into the future, it is most of the times, you don't really want a binary answer from a model. you actually do want some kind of an uncertainty estimate coming out of the model, which means you actually care, how certain is your model about this prediction into the future. If it has a prediction, say a 51% probability that it's going to rain, versus another, a situation where it gives you a 97% probability that it's going to rain, you want to kind of treat those two predictions, differently. If you just think of it as a classifier, both of them will be classified as y equals 1, right? But when you're trying to make decisions about the future, or in general, you many times you actually want this uncertainty estimate as well, right? And what do we do if it is not calibrated? So there are techniques to recalibrate a model. So there are some techniques to recalibrate a model. One of them is called Platt scaling, or you can also use something called as isotonic regression. So these techniques are you can think of them as post-processing, which means you fit your model to predict the y-hats what they produce, and then you take these y-hats as an input to a new model to learn some kind of an adjustment factor to adjust y-hat to be an updated y-hat, and that updated y-hat will be better calibrated using these techniques. This question.
So you said that this is like after you have fed the model, you do these kind of techniques. Can you do something like this where when you are trying to fit the model, you constantly take your loss function and then you constantly take your slope and then some weightage of that loss function and some weightage of, so if it's close to 45 degrees, you give it a higher weight and then combine those two?
Yeah. So the question is, can you kind of consider this slope and incorporate the slope of the calibration curve into the loss function somehow? So it so happens that the calibration is a probability of both your model and the test set against which you are measuring it. So which means if you train your model against, in say an environment where it mostly is say a desert-like an environment, and you fit your model there, and you want to now use your model in a different setting where it's some kind of a tropical island where the weather is very different, but you still think that your model has good discriminative ability of deciding rain versus not, then you can take the same model that was fit on a different data and just recalibrate it to using these techniques to data from say a tropical island, for example. So you can so you may not have access to the eventual test set against which you want to calibrate at the time of training.
So a decision boundary will still be the same, it will only scale up or down theta like.
Yeah, so these techniques generally do not reorder the points. They just perform some kind of an adjustment such that the ordering of the predictions will still be the same, but your model will be calibrated. Yes, question?
Are they necessarily linear? Can they be non-linear?
So Platt scaling is linear, isotonic regression is not linear. But they still maintain the ordering. Yeah. This question.
Does changing the threshold value have any effect to the calibration process?
Does changing the threshold value, what threshold of what?
Of the y-hat. So for like a classifier, you know how you have like a threshold of 0.5.
Yeah.
If you change that value, does that also change the outcome of the graph?
Good question. So the question is, does the threshold that we use for the classifier, does that affect calibration? In fact, the answer is the other way, right? So for calibration here, we are only plotting predicted probabilities versus true observed frequency. There's no threshold here anywhere, right? Once you recalibrate your model, you will almost certainly want to choose a new threshold to get a classifier out of it. Yes, question?
Looking at that graph, so that this is the graph after looking at which you should decide what is the appropriate threshold, right?
So this is not the graph to choose thresholds. This is to check whether the predicted probabilities can be thought of as probabilities.
And how do you decide what is the informed choice for a threshold? How do you make a choice for a threshold?
So we'll get into that probably tomorrow or day after when we talk about evaluation metrics, about how to choose thresholds. For now, we are just talking about calibration. Yes.
In your experience, out
How often is this done in practice? Looking at a calibration plot?
Like not in research, but in practice. Yeah.
Oh, in practice, extremely commonly, this is done in practice. Anywhere, anytime you want to take a prediction from a model and take some action based on it, in fact, I would call this closer to practice than closer to research. You always want to check, especially if you're constructing some kind of an application pipeline where you take decisions automatically based on the model's output, then you want to make sure that your model is well calibrated. Yes.
So I guess the reason we are doing this is to again maximize accuracy, but accuracy in a different way, where accuracy is not just like comparison of our predictions.
So the calibration is completely unrelated to accuracy, and let me show you why. Calibration, you may have a perfectly. So let's see. So the question is, calibration, is it equal to accuracy? Right? Or is there any relation between the two? If your model is very accurate, should it also be calibrated? If your model is perfectly calibrated, should it also be accurate? Any guesses? So if your model is perfectly accurate, should it be calibrated? Any guesses?
Yes.
No? Okay, I heard some no's and some yeses. If your model is perfectly calibrated, should it be perfectly accurate?
Just threshold it to like the same thing, 2 zeros and 1s. It will be accurate perfectly, but it would not be calibrated at all.
Now the question is the other way. If it's perfectly calibrated, should it be accurate? Yeah? Feels like? Right? So the answer is no for both. So here's an example. Supposing you have a data set where you have an equal number of positives and negatives, and let's say your model assigns probability of correct example. Let's assume is always 0.51, just above the threshold of 0.5, and probability of wrong is equal to 0.01. Now this model is perfectly accurate. It assigns a probability of 0.51 for all the correct examples and a probability of 0.01 for all the wrong examples. But if you plot the calibration plot, it will be for all the smallest bins, it will be close to here. But for all the examples that were at around 0.5, it will be here. But your calibration plot should be a straight line. Right? So in this example, the model is perfectly accurate, but it is not calibrated. What about the other way? Let's consider an example where half the examples are positive and half the examples are negative. And now we want to ask if a model is perfectly calibrated, is it accurate? Right? Now again, you can think of this example where the model assigns P of example to be equal to 0.5 for all examples. This will be perfectly calibrated, right? For all predictions that had a 0.5, the true frequency will be close to 0.5. Such a model will be perfectly calibrated, but will have zero accuracy because it's assigning the same probability to all examples. So calibration and accuracy are kind of distinct concepts. They're not necessarily related to each other. Yes.
So you said that whenever you are developing an application pipeline, you want to make automated decisions, you do this, but then it has nothing to do with accuracy. So how is it going to guide your decision making through any process?
Yeah, so this alone will not tell you whether your model is accurate or not, but this should be something that you look at, right? So generally a common thing to do is look at the calibration plot in relation to the histogram of probabilities, right? So take the set of all y hats and just look at the histogram of how your model assigns probabilities, right? If your model is well calibrated and your histogram of probabilities look like this, then you're in good shape, right? So the model is you call such well models. You call such models where you have a peak to the left and peak to the right as a model that is discriminating well. It's kind of sharp in its predictions. Its predictions are confident. It either produces a very low probability or a very high probability, and if it is calibrated, then you have a good model, right? If your histogram of predicted probabilities look like this, then your model is not very confident all the time, and if it's not very confident and then you don't have good discrimination power, but it may still be calibrated, right? So in practice, you want to look at both of them simultaneously. We'll come to ROCs probably tomorrow or on Friday. Right? All right. So calibration. So now the question is there how is this related to maximum entropy that we talked about, right? So as we mentioned earlier, the maximum entropy principle tells us that the choice of the probability distribution that we estimate should be as uncertain as possible, subject to some constraints that we have, and that will naturally lead to probability estimates that are well calibrated. Why is that? Let's see. So maximum entropy, we saw earlier, leads to maximum likelihood, right? So maximum entropy implied maximum likelihood, and in maximum likelihood, the objective of interest is this, right? So in MLE we did right. So if x is the predicted probability, then what we do is we use log p of x or the negative log p of x as the loss, right? So loss with respect to theta, right? We use this as the loss. Now to understand the connection between calibration and MLE or maximum entropy, we want to rethink the notion of loss function a little bit, slightly, right? Generally, we think of loss function as a function between y and y hat, where y is the observed or the ground truth or the correct answer, and y hat is our prediction, right? However, to kind of get a better understanding of calibration, you want to instead think of this scoring rule. So scoring rule that takes two inputs, a probability function p hat and y. So y is still the true observed outcome, and p hat is our predicted probability distribution. Right? P hat is not a point estimate, but it's a predicted probability distribution. It so happens that in logistic regression, the single point estimate probability defines the full probability distribution. But in general, if you are, for example, in a regression setting, think of this to be a full Gaussian distribution, like the mean and variance of a full Gaussian distribution, for example. Right? So this is a probability distribution over all possible outcomes, right? And this is the actual observed outcome. Right? So our model will output p hat, a full probability distribution over all possible outcomes. So if we are some kind of in a weather forecasting setting, for example, this will give a probable, and let's say we are trying to measure, say, wind speed of tomorrow, for example, then this will give you a probability distribution that it's going to be have a 5% probability that the wind will be 10 miles per hour, 7% probability that the wind speed will be 15 miles per hour, and so on. It's going to give you a full probability distribution over the entire outcome space, right? In case of a binary decision of whether it's going to rain tomorrow or not, if the outcomes are only two, all what you care is will it rain or not rain, you don't care how much it rains. If that's the space of outcomes, then the outcome is 30% that it will rain and therefore 70% that it will not rain, or 50% that it will rain and therefore 50% it will not rain. So it's the full probability distribution over the space of outcomes. We are not assuming a Bayesian setting. All that we have is some predicted probability distribution and one observed outcome, right? And the next day we'll again output a full probability distribution and there'll be some one observed outcome.
In classical setting, we always have 1 point estimate, right?
The difference between Bayesian and frequentist is how we treat the parameters. Here, this is just predictions, right? This is not Bayesian versus frequentist. This is more general. So now we have this notion of what is called as a proper scoring rule. A proper scoring rule is one that satisfies this requirement. So let's call a proper scoring rule, let's call it F. So F is a proper scoring rule if it satisfies. So proper scoring rule F, where F takes a probability distribution, an outcome, and maps it to a real value. Right? A scoring rule is one that takes the observation made by a forecaster and then observes the actual outcome, looks at those two, and assigns a score of how well the forecaster did. Right? You want to think of the scoring rule that way. So it takes a prediction, a full probability distribution, one observed outcome, and assigns a score. Right? And a proper scoring rule is one that satisfies Q So a proper scoring rule F is that scoring rule which satisfies this inequality, that the expectation of f of q comma y, where y is sampled according to q, is less than equal to expectation of f of p comma y, y sampled to q, for all p and q, and you call it a strictly proper scoring rule, strictly proper scoring rule, where equality implies p equals q. Right? What does this mean? So let's try to understand this a little better. So we have two instances of the scoring rule being called. The scoring rule, as I said, takes a prediction and an actual outcome, right? Prediction and an actual outcome. F is a proper scoring rule if when the actual outcomes follow a distribution Q, actual outcomes follow some distribution Q, the average score assigned by f for a prediction q itself, where q was how the actual y's were distributed, will be less than the average score assigned by f where the prediction was a different distribution p than how y was actually distributed. Right? Now, if f is used as a loss function for your model and f is a proper scoring rule, then your models will tend to be well calibrated. Why is that? That's because the proper scoring rule naturally rewards q to have the best possible score when q was the distribution according to which y's were getting observed from. Right? So y tilde q here and y tilde q, you want to think of this as, q being the way the weather is actually modeled, and y's are therefore sampled according to the way the weather is actually happening in real life. And the probability distribution that's passed to f is the prediction that we are making. Right? The best possible prediction is when we predict the true weather itself as our prediction. Right? For any other prediction which is not the actual weather, then it will get a worse score according to this scoring rule. If this satisfies for all p and q, then f is a proper scoring rule. Next question.
Can you explain why any other distribution have a greater expected value?
So here you can think of this as loss. A higher loss is worse. So we want f to assign low values for better predictions. Right? Yeah, I'm going to come to that. Right? So this is a proper scoring rule. Right? Now, from this, it's easy to see that if we recover, if we recover the best possible prediction, then our model is naturally calibrated, because the best possible prediction is q itself. Right? So the best possible prediction that we can do is to predict q, because that is the lowest loss that can be attained. And so, using proper scoring rules as our loss functions will encourage our models to be better calibrated. Does that make sense? Any other p other than q will attain a worse loss compared to predicting q itself. And when you compare, when you predict q itself, your calibration curve will be a straight line, because depending on if y's are sampled from q such that it is 80%, 80%, then we want to predict 80%, and that would be because that's the best thing to do according to the scoring rule. Does that make sense? Yes, question?
Now I don't understand why well-calibrated model doesn't mean that it's accurate, because from this it seems like you are getting at the distribution at which y is being distributed.
Yeah.
By doing a well-calibrated model, which implies accuracy, right?
This does not necessarily imply accuracy. So the question is, does this imply accuracy? It need not, because what we are looking for is, the average scores in the long term. So supposing it rains 50% on average, right? Your predictions may be such that half the time you predicted it will rain, but half the time you will predict it will not rain. And in the long running average, you may match the frequencies, but on every given day you may end up predicting the wrong thing, right? So this is not related to accuracy, right? So a proper scoring rule will encourage your model to have the long run frequency match the predicted frequency, or the predicted probability. And now the question is, how is this related to maximum entropy? So first, do we have a consensus on this, that if we employ a proper scoring rule, because of this property of proper scoring rules, the predicted probabilities will tend to be calibrated. Or is there a question on that? Yes, question.
When we were just looking at the loss function which took just the y and y hat, if you had like, if you took the theta which was from the data generating process, then also it will have a better estimate over the predicted theta. So why not use that directly? Because it also follows the same inequality.
I'm sorry, I didn't understand the question.
So y and y hat in that, like the loss function, y was from a data generating process, and when we calculate y hat, we make an estimate of our thetas. Even in that case, our inequality was the same. The loss would be less than our given loss.
What do you mean by y hat?
You wrote about squaring rule loss no, on the left side.
On the left side? Yeah. Yeah.
Below this line. So you have
Yeah.
this function, right?
Yeah.
If you directly use this loss function, where y was from a data generating process and y hat was theta, our estimated theta transpose x, you have the same inequality like that, where
Well, may or may not, right? So the question is, if we use a loss value like this, where y hat was just theta transpose x, will we get the same inequality? So in case of logistic regression, y hat completely determined the entire distribution, but in case of regression, that's not the case. If you just have a point estimate, it's not a distribution over all the possible y's, right? So in case of logistic regression, y hat or the point estimate of the probability is the full distribution, right? But that's not the case in more general settings like regression, right? So now the question is, so assuming that we have a consensus that employing a proper scoring rule encourages our model, encourages us to recover the true probability distribution, in which case the models will tend to be calibrated. Now the question is, how is this related to maximum entropy? So in maximum entropy, we saw that maximum entropy gives rise to MLE, and MLE is essentially this. MLE, the loss is y coming from Q and minus log 1 over P. Right? So this is the so this is the loss, or let's think of this as like the true loss. So this is the true loss of maximum likelihood, where y is distributed according to some data generating distribution, and the loss that we have is the negative log likelihood, or sorry, this should be log p hat, right? So the model predicts p hat, but the data is distributed according to y. The loss is the negative log likelihood under the expectation where y hat is distributed according to Q. Now what remains to be showed is this is a proper scoring rule. Right? So minus log p hat of y, sorry. Right? So y's are the zeros and ones, they are sampled according to Q, and p hat is log p hat of y, so p hat is the generated is the predicted probability, and we want to evaluate y according to this, right? So what remains to be showed is this is a proper scoring rule, and the way we show this is a proper scoring rule is pretty simple. We want to show this inequality, right? So expectation of y according to Q minus log Q of y should be less than or equal to expectation of y according to Q of minus log P of y, right? And we take this to the right hand side, and this we get 0, or we want to show this is less than this. Yeah. So we take it's greater than equal to 0. Yeah. So we take this to the right hand side, and we get is equal to expectation y according to q log. So this is minus log. So this when it comes here, it will be plus log. You get log q of y over b, and this is negative. So this is 1 over p over py. So we need to show this, and this can be easily shown because this is just the KL divergence between q and p, and that's always non-negative. Right? So the maximum entropy principle is equivalent to maximum likelihood estimation, and the maximum likelihood estimation uses negative log as the proper scoring rule, as the loss function, and this loss function, due to KL divergence being non-negative, implies that it's a proper scoring rule, and because it's a proper scoring rule, the estimated probabilities will tend to be well calibrated. Right? So that's like the multi-step connection between maximum entropy and calibration. Right? So maximizing entropy is therefore leads to your model being well calibrated. Yes, question.
Why do we use so from now on, if you have to fit logistic regression, do we use this loss function or?
So this is the loss function that you've been using for logistic regression. This is the same thing that you've been using for logistic regression. It's no different.
So for other function, like is there anything different that because in our it's the entropy loss, right? Cross entropy loss.
Yes, this is the cross entropy loss, and that is the same as the maximum likelihood estimation. It's the same loss. You can work out the math. They're exactly the same. Right? There are other kinds of entropy measures that you can use. So here we used, for maximum entropy, we used, the Shannon's entropy. That's p log p. There are different kinds of entropies that are there, not just Shannon's entropy. And by using a different kind of an entropy, you get different kinds of a divergence rather than KL divergence, and you get a different loss function. And all those will still be will lead to calibration models as long as the scoring rule that you get is a proper scoring rule. That's the general takeaway in this. All right. So we're out of time, and we'll start with the EM variants and the variational autoencoder in the next class. Right. Thanks.